Did the late bell even ring, or am I starting class early? Alright, everybody's here, so I'm getting started. This is on side 2B where we left off. This is just some right triangle trig. A lot of these problems on the quiz are application problems, okay? So we have a submarine that's 250 meters below the surface of an ocean, begins to ascend at an angle of 22 degrees from vertical. How far will the submarine travel before it breaks the surface of the water? Okay, so we're going to assume the water is basically horizontal, right? And there's a submarine down here, which clearly looks exactly like that. Now what? Okay, so we have a vertical distance down. Yeah, straight down, obviously. I'm leaving something to be desired with my directions today. That's supposed to be making a right angle with the water. And then it says it starts to go up. So this guy turns and he's headed towards the surface over here somewhere. We're supposed to figure out where to put this 22-degree angle and how far it travels till it breaks the surface. So where to put the X? From verticals. So yeah, we got the vertical line here. It's so crooked it doesn't look vertical, I know. Then we're going to put 22 degrees there. Okay. Where's the sub actually going? He's following this funky line right here, right? So that's the distance we want to find. The hypotenuse, even though it doesn't look like one in my picture. All right, which function do we need? Hypotenuse and adjacent, which would mean cosine. 22. What mode do we need to make sure we're in? Okay, and it's adjacent over hypotenuse. So when we go to type it in, we need to type 250 times 1, or 250 divided by cosine of 22. $22 degrees. Does that sound too steep? I don't have any idea. I just know submarines from watching movies. You guys ever watch Hunt for Red October? It's a really old Sean Connery. It's not really old, but it's a Sean Connery movie. At one point he was, yes. All right, any questions? We good? Denzel Washington is in that movie too? I don't know, now I'm just off track totally. Okay, can you guys try this one on your own? How far up does the ladder reach? So we're looking for this distance. The ladder and the ground are the angle over here is 70.1. And part B wants to know how far the bottom is of the ladder out from the building. So we need to find X and Y. Riley, you remembered all this stuff? Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Remember that business? Okay. How about if you try these then? Anybody get an answer for X? And how far out is it? This seems a little odd to me. 10.2 feet? That seems kind of far away to have the base of your ladder, but it's a very long ladder. A 30-foot ladder would be like a 3-story ladder or so. It's pretty far, pretty long. All right. What's wrong? Are you in the wrong mode? Oh yeah, for part 30 squared minus 28.2 squared. If you want to use Pythagorean theorem to find part B, it would be on this picture, it would be x squared plus y squared equals hypotenuse squared. So 30.
Okay, you just like because the rounding is different because you round like two rounds. So I got 10.8.
What? Can't be that off, is it?
Otherwise we're having 20.
Yeah, I still got 10.2 when I did Pythagorean theorem. So, all right, guys, we need to talk about angle of elevation and depression. Very important. Both of these are from the horizontal. So an angle of elevation is from the ground up. An angle of depression is like if you were standing at the top of something looking down. They are both made from the horizontal. Oh, I don't know what that says. Okay. Never with a vertical line. What you will notice, if you were to draw them both on one picture, they are equal to each other because these are parallel, being horizontal lines, and these are called alternate interior angles, so they are equal to each other, okay? What you cannot do is say here, this guy's standing up here at the top of the world, and his angle of depression is 6 degrees or something. You can never use a vertical line, okay? Don't ever put it with a vertical line. Do you see what I'm talking about? Angle of depression would be here, not the vertical line, okay? That would not be an angle of elevation or depression. If it was with a vertical line, it doesn't ever count. So what I'm saying is if there was a picture where it said he's standing up on top of the building and he has to look down 6 degrees, or angle of depression is 6 degrees, it's always here. It would not go here. This is inside of here is never an angle of depression or elevation. It's got to be against the horizontal line. Does that help? Okay. Here we go. This time, a person is standing on top of a cliff. Oh, rough cliff. Okay, here's our cliff. He is standing, he actually is 100 meters, 100 feet away from the cliff. And when he looks up to the top of the cliff, it's 30 degrees. Okay? Then he's standing there, he goes, wait, what if I look up a little higher? I actually see not only the cliff, I see what? A tower on top of the cliff. There's his tower, okay? And if he has to look up to the top of the tower, it's 58 degrees. So if I find this height, I will have the cliff. If I find this height, I will actually have what? Cliff plus the tower. So how can I find the tower? Subtract those two answers. Okay? We could use law of sines or cosines, maybe, if we remembered those, but I haven't touched those, so we're pretending we don't remember those. So this would be the tangent of 30 equals opposite over adjacent, or the tangent of 58 equals y, opposite over 100, and then we're going to subtract those two answers to find just the cliff. Is it coming back, Riley? So y minus x will give us the cliff, or the tower only, right? We already know the cliff. We're looking for the tower, my bad. I think I said it wrong a second ago. Which is 102.3, is that right? Label? Okay. So on the homework in the book, I think there's quite a few application problems you have to do. On page 120 or 227, my bad, 227. On the quiz, there are also quite a few applications, and for the majority of them, the picture isn't drawn. You have to figure out how to draw the picture, okay? So you have to know how to read carefully. Now we are switching over to worksheet 5. The first part of the lesson is review. I'm going to talk a little bit about some new stuff, degrees, minutes, and seconds, and decimal degrees, and how to convert back and forth. And then we're going to start on the new stuff, which is probably not new to most of you, angular and linear velocity. Is that easy for me to say? Okay. I'll try again. All right. So the first thing I have on a slide here is just really quick review. If you have a coordinate plane, the initial side is always on the positive x-axis. If you measure around counterclockwise, it's positive. If we were to go around this way, it would be a negative angle. Where it ends or where you stop measuring is called the terminal side. Okay? So if we had something like I told you to draw a negative 700 degree angle, you would start here, go this direction, 360, and almost to 720, which would be almost to twice around, right? 720 would be twice around. So you'd be left with a 20 degree reference angle. We're going to talk about those next week. We good? All right. Converting between degrees, minutes, and seconds. Not going to use this very often, but I am going to show you how to do it on your calculator in just a second. There are 60 minutes in every degree, and every one of those minutes is split into 60 seconds. It's kind of like hours, minutes, and seconds. Make sense? They use this a lot, like, or supposedly they use it in navigation or in surveying. They don't necessarily use decimals. I find it hard to believe they don't use decimals, honestly. But all right, so what you would do if you were doing this by hand, if I was a meanie bobini and made you do this by hand, you would say this is 56 degrees plus an extra part that is degrees. If I want to change that to minutes, there's 60 minutes in 1 degree. So if I do a little dimensional analysis, somebody type for me, 0.735 times 60. Okay, that's 44.1 minutes, which is written like this, 44 minutes. Use like feet, it's minutes. I don't know. So, yeah, degrees, minutes, and seconds is like hours, minutes, and seconds, only we use the little labels for feet and inches because that makes it so much clearer. All right, I'm taking off the 0.1 because the 0.1 of a minute needs to be converted to seconds, and every minute is 60 seconds. So 0.1 times 60 is 6. So we ended up with 56 degrees, 44 minutes, and 6 seconds. Let's learn to do this on our calculator because it's way faster.
Why would you call them minutes? Why would you give them a different name?
I don't have that answer. All right, so we're going to put 56.735. And then we're going to go to the angle menu. Do you see it up here? It's on the apps key. So you're going to go second apps. Find it? Second apps, the angle menu. Choose choice 4 because we want to change this into degrees, minutes, and seconds. Bam! Pretty easy? Okay. Yeah, the easy button. There you go. No? Didn't work? Did you get it to work? Okay. So can you do this problem right here for me? This one right here that's on your worksheet. 213.875. And you go second app, degrees, minutes, and seconds, which is choice 4. Bam. 213. 52 minutes and 30 seconds. Okay. If you're going backwards, in the good old days without a calculator, for this problem, I would have said I have 32 degrees plus minutes are 60ths of a degree, so I have 5/60ths plus, ooh, think about this for a minute. How many seconds in an hour? It's not 60. 60 times 60, yes, 3,600 seconds before you get to an hour. So that 28 seconds at the end has to be divided by 3,600. If you typed all that garbage in your calculator, you'd get this. It may be rounded, I don't know. So we don't want to have to do that, though it's really pretty easy. Okay. But we can type it in just like this and then hit enter and it'll change it to a decimal. The trick is that these two symbols are both in the angle menu and the seconds is not. Because seconds is actually the quotes, and you actually use quotes a lot when you do programming. So they're right on the front of your calculator. I think it's alpha and then the plus key to get the quotes. All right, so here I'm going to move this over so you can see one more time. We're going to type 89. You got to go to math, or the second apps again to get the degree thing, which is choice 1. And then you go 56, second apps, and get the minute thing, which is choice 2. And then you type 7, alpha, not second, just kidding, alpha plus to get the little quotes. And if we rounded to like thousandths, it'd be 89.935. I still think it would have been faster to go 89 plus 56/60ths plus 7/3600ths. But that's just because I had to memorize all that junk, and we used to do a lot of those kind, and we don't anymore. Everybody okay? So, may want to review that before quiz sometime, but it's really pretty easy. Okay. We're going to talk about the definition of radian real quick again. Applications often use radians because degrees have no relationship to linear measure. There's no such thing as inch per degree or inch degrees or anything. Okay? If you talk about the amount of distance here in the radius and the amount of distance here along the circumference, and you divide those, you get the angle theta in radians. You need to know that radians is a magical label that often disappears and reappears. Okay? When you end up with nothing over inches, it's probably radians per inch. When you have radians in an extra label, so you have like radians times centimeters per minute, it's probably the answer is just centimeters per minute. They just appear and disappear. It's just this magical, and it has to do with the fact that it's really just a radius, so it's a different distance that divides out. All right, we already covered this. Jacob, you awake? Need to get up and get a piece of candy. Degrees to angle, angles to degrees. Are we okay? We talked about that yesterday, so I can skip this. All right. This is talking about coterminal positive and negative angles. I am going to only talk about this slide for 1 second. This symbol, yes? This symbol, okay? This symbol is how Hofbauer draws a theta, okay? We will use 2 more today. This one, I think it's a little V, it's a upsilon or a lowercase gamma. No, it's not gamma. I don't know. We just call it V in this class because I don't know. And your book actually uses it as a capital V some of the time. It's going to be linear velocity. The other one they use is this, which is a lowercase omega, which we're just going to call W because it's angular velocity. It's actually an omega, but we're just going to call it W. Okay? As if I start calling it omega, everything. Well, which one's omega? Only ones you're really good at are probably theta, maybe beta, because it looks like a B. All right. They usually use reference angle as alpha. But yesterday we talked briefly about this, and we're going to go through it really fast again today. If you want all the coterminal angles in degrees, and you have a degree angle, you add 360 over and over and over to find all the coterminal angles. So we write plus 360n, where n is any integer. If it's in radians, what do you add? 2 pi n, where n is any integer. So super duper fast, because we did these yesterday already. We're going to write negative pi over 2. All coterminal angles would be plus or minus 2 pi n, where n is any integer. Why do they not write plus or minus on theirs? They only write plus. Why do they do that? N is an integer. Integers can be negative, right? Good job. So if you just put plus n and n was, or plus 2 pi n and n happened to be negative 6, it's the same as minus. So I always write plus or minus because that's the way I learned it, and because it reminds me that you can go either way, positive or negative. But I don't care. What do you do when it's degrees? Plus or minus 360 and I really don't care if you don't write any integer. So what would number 4 be? So Riley, yesterday when we did this, we talked about like find me a positive and a negative angle that are coterminal rather than finding all of them. Coterminal means that who can answer that question? Remember how I explained coterminal yesterday?
Coterminal means like when you draw the angles, they end up on the same side.
Yes. Co means together, like cohabitate, cooperate, work together. Terminal means it ends. So it means they end in the same place. Okay, together they end in the same place. So, for example, 90 degrees and negative 270 are coterminal. Does that help? Okay. Great question. I should have started with that explanation, but we did it yesterday. All right, guys, this is on your blue sheets. You may want to grab your blue sheet so you know where these are. A minute ago, they defined theta as the arc length divided by the radius. Well, if you want to find the arc length, you multiply the r over there, okay? So the arc length s is equal to r times theta, where r is the radius and theta is the angle in radians. Okay? This formula right here, though, is on your blue sheet. It's above the unit circle, I think. Did you find them? Above the unit circle are all the formulas we're going to be using right now. Are we good? All right. A linear speed is how fast something moves along a circular path. Okay? It is a distance. It is measured in units like miles per hour, it says. An angular speed, okay, is how fast something turns. You usually measure it in radians per time. They say here you could measure it in revolutions per minute. Then later on when they talk about it, they call it a, what do they call it somewhere else? They call it a rate of rotation if it's if it's not in radians. Okay, in order to be a linear speed, it needs to be some kind of distance divided by time. Okay, distance divided by time. So, and sometimes it will have that funny V instead of the regular V, just warning you. Okay, what are some labels of distance over time? Jacob, give me a distance and a time. Just a label, you don't need a number. And? Meters per minute. Miles per hour. Centimeters per second. Feet per second. Inches per second. We good? Okay. Angular speed, on the other hand, is how fast it's rotating. Okay? So it's measured in radians per time. So you might have radians per minute, radians per hour, radians per second. Okay? If they talk about revolutions per minute, or RPMs, we have to use a conversion. Okay, we have to convert it to radians. Do you know what the conversion is? 1 revolution is 2 pi radians. So if they said 6 RPMs, that would mean 6 revolutions per minute. And you would say 1 revolution is 2 pi radians. So the angular velocity would be 12 pi radians per minute. I think record player, because I'm old school, and RPMs, it had like 45 or 78 or 33 RPMs on the record label, but you guys don't even know what I'm talking about. Vinyl. You heard of vinyl? Okay. This one's done, so just watch. Humor me. Watch my beautiful handwriting, okay? It says 8.2 revolutions in 3 seconds. 8.2 revolutions in 3 seconds. That's not an angular speed that they want it to be, because we need it in what? Radians. So 1 revolution is 2 pi radians. So 8.2 times 2 times pi, and divided by what? There's a 3 down here, so we've got to divide it by 3. Yep, helps if you turn the calculator on. 8.2 times 2 times pi divided by 3. Yeah, I multiplied the pi in, sorry. 17.17 radians per second. Okay, now look at their answer. Did they have that somewhere? Okay. Second part asks us to find the linear speed. We haven't talked about this formula yet, but linear speed is actually angular speed times the radius, because we need it to be in distance. Is there a radius in this question? The distance from the center of rotation is 7. That's the radius, okay? Centimeters. So if we take our 17.17 radians per second, and we multiply it by that 7 centimeter radius, and what magically goes away? Yeah, the radian just disappears, so that we end up with centimeters per second. And that's the linear speed. So this one was linear velocity, and this one was angular. Okay, I really don't like these questions. The way they're worded is painful, and the directions are painful. It says, find the rotation in revolutions per minute, so we're trying to find RPMs, given an angular speed, and the radius if you're given linear speed and rate of revolution. Why wouldn't they just split it into 2 sections, okay? The first 3 questions, they give us the angular. The second 3 questions have to do with the second part of the directions. All right, this is just dimensional analysis. Help me real fast. 2.7. Yeah. What do we want? Revolutions per minute. What do I need to do to get this to revolutions and minutes? Revolutions, radians. Usually we're going the other way, but this one, 1 over 2 pi, because we want the radians to cancel. We want minutes. 60 seconds goes up here so that seconds will cancel, and we'll end up with minutes in the denominator. So our labels that are left are revolutions and minutes, which is what we want. And we have 2.7 times 1 times 60 is being divided by 2 pi. You get the wrong answer 90% of the time here. Why? Why is everybody going to get this wrong when they type it in their calculator? Yeah, if you type 2.7 times 60 divided by 2 times pi, it's going to do all this and then multiply by pi. You want the pi to be divided, right? So it's in the denominator. I would just put parentheses here. You can hit divided by 2 and then divided by pi and it'll work, but so just remember when you're dividing by 2 pi, you have to do parentheses. 2.7 times 60 divided by parentheses 2 pi. 25.8, anybody? RPMs, revolutions per minute. Okay, 4 pi over 3. The label is radians per hour. You can put it on the whole thing, or you could actually say it's 4 pi radians in 3 hours. It's the same difference. What do we need to do? We want revolutions per minute. Radians, revolution, what else? Yeah, we need hours. 1 hour is... They want minutes, though. It says revolutions per minute, so we need an hour is 60 minutes. Okay, yeah, it is. It's just dimensional analysis, just like chem. We have 4 pi on the top, and on the denominator we have a 3 and a 2 pi and a 60. Yes? So what happens? I'm going to just reduce this. I get 2 over 180, which is 1/90th, or is it? Did you forget parentheses? What? 0.01 is the right answer. Okay, guys, if you wanted, watch, you could type this in, and then you could say I need to divide by this, and I need to divide by this, okay? But when you divide by the 2 pi, you need parentheses. So if you want to do 4 times pi divided by 3, then divided by parentheses 2 pi, and then that answer divided by 60, you get 0.01. It's 1/90th. Or 1 revolution every 90 minutes. That's pretty slow, huh? 1 revolution every 90 minutes. I know that's what it feels like some days. Like the second hand only goes around once every 90 minutes, or the minute takes like an hour and a half before it goes. Slows time down. Okay. Do we need to do this one? You got this idea or not? If you want to do it real fast, I'll just write down what it would be. Radians per minute. All we need, oh, this is already in minutes, right? So we just need to divide by 2 pi. So we'd end up with 3 pi radians over 4 pi minutes. 3/4 radians per minute, or 0.75. Okay, moving on. This second set, this is like a whole new set of directions now, starting with number 8. It says, find the radius given the linear speed and the rate of rotation. Okay? This is a rate of rotation. It is not an angular speed yet. What do we need to do? Rotation. I can't spell. We need to change it to radians. So 120 revolutions per minute. Where's we multiplying or dividing by 2 pi this time? 1 revolution is 2 pi radians, so we're multiplying. So we end up with 240 pi radians per minute. That sounds really good until you look up here and you realize that this linear velocity is in meters per second. Ugh! All right, let's change this to seconds. So 1 minute is 60 seconds. What's 240 pi divided by 60? 4 pi? Okay. Radians per second. And I'm going to go with that's our angular velocity, because that's what they asked for. Now we need to find the radius. Does anybody remember the relationship that I wrote down? Nice. Okay, it is on the sheet. We're trying to find r, so what do we have to do here? Okay, so we have 24.8 meters per second is divided by 4 pi, which we could have made 12 point whatever, radians per second. Okay, per second and per second will go away. Radians will magically disappear, and we will have what label? Meters. The radius is, okay. Yeah, it's almost 2. 1.97 meters. Don't forget the parentheses when you divide. What? Yeah, it's 2. How are we doing? Okay. We're going to quit early, I promise, okay? Let's get these 2 done. Maybe even 11. We'll see how fast we can go. Okay. Do you want to hurt me right now? I promise we're not going to go on to the next worksheet, but let's try to get these done. 3.6 revolutions per second. We need it in radians, and because of the velocity, we probably also want it in what? Minutes. So let's change this to radians and minutes. 1 revolution is 2 pi radians, and 60 seconds is a minute. Oh, this one's all on the top, right? So we can just multiply. 3.6 times 2 times pi times 60. What are the labels left? Radians per minute. And we didn't need to change it to minutes. We could have changed this one instead, but eventually we need to be doing this, and we needed them to have the same labels. So we have 118 feet per minute divided by 1357.2 radians per minute, 4.17, whatever you want to do. And that will give us how many feet? About 0.087 or something. We could have reduced it all out and seen what happened, but I'm just, whatever. Yeah, we could multiply by 12 and make it inches. Okay. What does this one say? Almost done. We have half or 0.5 of a revolution per minute, and we want it in hours. So 1 revolution is 2 pi radians, and 1 hour up top, no, I lied, 60 minutes up top is 1 hour. So 0.5 times 2 pi times 60 sounds to me like 60 pi. Did I get that right?
Yes.
Because half of 2 pi is 1 pi times 60, so I have 60 pi. What was our label left? Radians per hour. Oh, forgot the pi, thank you. I like pi. We should never forget the pi. Okay. Linear velocity has to be divided by that. So we have 256 inches per hour divided by 60 pi, which we need to put that in parentheses, radians per hour. What'd you get? 1 point? Label? Just inches. Nope, because the per hour and the per hour here divide out. If we were to flip it over, because when you divide, you really do a reciprocal, right? You'd have inches per hour times hours per radian. The hours would divide out, yeah. You know what, guys? I know you hate that I do this, but can we just finish this worksheet? Because I didn't finish it in the other two classes, but if I can finish it on the same recording, that would be really helpful, right? Because it's the end of a worksheet. Don't hate. Okay, how much longer is the outside? We need arc length here, okay? I'm going fast. I'm telling you what we need. We need arc length. How do you find arc length? S equals R times theta. But theta has to be in radians or it doesn't work. So it says a curve on a highway has a 1,000-foot radius with lanes that are 14 feet wide. We're going to say that 1,000 feet is the inner radius here. So we're going to do 1,000 times, how are we going to change 90 degrees? 90 times pi over 180 or pi over 2, yes? Okay. But it says if a curve makes 180 degrees, how much longer? Oh, we got to use 180. I lied. So 180 is just what? This is easier, guys. Pi. Okay. So we have the arc length is 1,000 pi feet if you were to walk along the very edge. If you go way out here, how much further have you gone? Well, be careful. Each lane is 14 feet, I think. So that would be another 28. Okay. Do you see? It says each lane is lanes that are 14 feet wide. Yeah, that's a pretty wide lane, isn't it? I don't know. So we're going to go the arc out here, guys. Shh, the arc out there on the outside is 1,028 times the radius or the radians of 180 degrees, which is pi. So the difference, how much further did they go, would be 28 pi, which is approximately, how about 88 feet? 28 times pi is almost 88 feet. Now, it's not actually that different because you don't actually travel along the very edge on the inside of the road or the very edge on the outside. Okay, you kind of go down the middle of each lane, but it is a big difference. At the end? Because it was a 180 degree turn, not a 90 degree turn. They wanted to know how much difference you travel if you do the whole 180 degrees. Yeah. You had to read that part carefully.